So section 4.1, there were two sort of big ideas in that section. The first was how to find critical numbers, and the second one was to use those critical numbers to find maximums and minimums of a function on a closed interval. So first of all, how do you find critical numbers? What do you do?
Find the derivative and the second derivative and set them both equal to 0.
Just the first derivative equal to 0. So the critical numbers are where the first derivative is equal to 0, and one more thing about the first derivative. Where f prime is undefined. So critical numbers are places where that occurs. And you could have maxima or minima at those critical numbers, but you don't have to. And then how do you find the absolute max and min on a closed interval? So step 1 is you find the... And then steps 2 and 3 is that you plug the critical numbers, I'm going to call them Cn, and the endpoints. Where do you plug them into? Into F. And then you compare. And the thing that you're going to forget, if you forget anything, is you're going to forget that the endpoints are also potential maxima and minima on that closed interval. Okay? And that's really the two big ideas in section 4.1. That's really was it. Okay. So let's find the critical numbers of this function on the interval from 0 to pi. So find the derivative, which is... Nope.
Minus, no.
Do it in 2 steps, okay? That really is cosine of x squared, okay? So chain rule it. It's plus...
plus 2 cosine of x.
Times...
Negative sine of x.
There you go. Don't rush it quite yet, because you guys just, you just need to get a bit more practice before you can do it all in your head. Is that okay? Set it equal to 0. So equals cosine x minus 2 cosine x sine x. Take out the greatest common factor, which is cosine x. So far, so good? Okay. So when is 0 gonna equal cosine? And when is 0 going to equal 1 minus 2 sine? If nothing else, you guys have gotten better at triggering the unit circle. So where is cosine 0 in between 0 and pi? Pi over 2. Yep, and only pi over 2 in this case because we're only looking for in between 0 and pi. So no need to say plus pi in. This next part will be 1/2 equals sine, right? And that will happen in quadrant 1 and quadrant 2, right?
That's pi over...
It's either that one or that one, right?
Yeah. Yep.
Pi over 6.
And 5 pi over 6.
Very good. Yep, pi over 6 and 5 pi over 6. Is that all right? Okay. Your quiz and your review packet will have more examples of things like where the... Definitely not. Because you'd take away 1 and then divide by -2. Your review packet has examples of places where the derivative is also undefined, so make sure you pay attention to those. Okay? So that just can't do every single example in class. Okay. So find the maximum minimum values of this function on that specific interval. Okay, so first thing we do is find the derivative, set it equal to 0. So what rule do you need to differentiate this function?
The chain rule?
The chain rule, good. So that'll be 3 times x squared plus 2x to the
Seconds?
times
2x plus 1?
2x plus 2, I believe.
Yeah, I misread that.
That's okay, it happens. Set it equal to 0. 3. I'm going to write that thing inside the squared as x times x plus 2, the quantity squared. And then this is 2 times x plus 1. You don't have to do that, but it just makes it super easy to see what the zeros are. So where is this derivative equal to 0? Mm-hmm. Mm-hmm. Do you guys agree with that? All right. Now, at this stage, this is just a thing to be aware of. Check if they are in the interval. Because if they're not in the interval, they're not even candidates for maxes and mins. And although in this case, I think they are all in the interval, and one of them happens to be an endpoint.
Yeah.
So, no worries there. And then test all of them. Test f of -2, f of -1. I just put them in ascending order because it makes me know I've done all of them. And you plug them into the original, because if you plug them into the derivative, what are you going to get for all of them? All but one, actually. You're going to get 0 for all, because that's where the derivative is 0, right? Okay, so when you plug in -2, you get 4 minus 4 cubed. I think you get 0 for that one. Okay. When we input -1, that's 1 minus 2 cubed, which is going to be what? -1. How about when you input 0, what do you get?
Yeah.
When you input 1, you get
8? No.
20, yeah, you get 1 plus 2 cubed, or 27.
Yeah, 1 cubed. 1 squared is 1.
Yeah, exactly. So f of -1 equal to -1 is the absolute min. And f of 1 equal to 27 is the absolute max. Okay. All right, the Rolle's theorem and mean value theorem questions that you're going to be asked will be similar to the questions that you were asked in your quiz, which were things like figure out what numbers satisfy the conclusion of Rolle's theorem, figure out what numbers satisfy the conclusion of the mean value theorem. So the Rolle's theorem and mean value theorem began the same way. You assumed you had a function f that is continuous on the interval from a to b and differentiable on the open interval. And that's the same thing for the mean value theorem. And I just want you to tell me that you know that those two things are necessary. Just that the assumptions are, okay, this function is continuous and differentiable. Just state that that's the case. You know, polynomials are, trig functions are, even like a logarithm function is, as long as you're within its domain. There's no, the continuous means there's no breaks. The differential means there's like no corners in addition to the no breaks. Rolle's theorem had one more assumption. Do you remember what it was? Yeah, f of a equals f of b. And I called that 3 because 1 was really 1 and 2. And that assumption isn't, it's not because I can't count, even though that is occasionally true. And here's what the conclusion said. Conclusion. Said if those thing happens, then f prime of c has to equal 0 for some c in between a and b. And so for those questions that we did in class, you need to figure out where the derivative is equal to 0 in your interval from a to b. And that might just be one number, there might be many, but those are the places where the conclusion is met. And the picture there is that if your endpoints are equal, the y values, your function has to have some kind of turnaround point in the middle where the tangent line is horizontal. That's what this is saying. So it's just the numbers that satisfy the conclusion of Rolle's theorem is just saying, okay, what numbers give the derivative being 0? That's all. the mean value theorem didn't have that last conclusion, or that last assumption. So here what the conclusion said, f prime of c equals f of b minus f of a over b minus a for some c in the interval a, b. And so here what you're going to do is you're going to find f of b minus f of a over b minus a. It's going to be some number, probably not 0. And then you're going to set f prime of c equal to that number, equal to, not 0, equal to this thing, and solve. So instead of asking where the derivative is 0, maybe asking where is the derivative 5, or 10, or -2. It's the same principle, it's just that you're setting the derivative equal to a specific number. And officially, the picture for this one is something like this. You have some unequal y values, let's assume they're unequal, function that goes between them. The f of b minus f of a over b minus a is the slope of that secant line. It's the average rate of change, or you think like your average speed. It's saying somewhere in the middle, your velocity is the same thing. And if you draw that same picture in the one above, notice how the tangent line, or the secant line, actually is a line with slope 0. It's the same idea, right? It just happens to be equal to 0 specifically. So looking for where a derivative is 0, looking for where a derivative equals some number that will be different in every case. Okay, and could theoretically even be 0, but I probably wouldn't do that to you. Okay. So figure out whether Rolle's theorem applies to this on 0 to 2 pi, and if it does, find all numbers that satisfy the conclusion. So I'm going to change this a little bit. I'm going to do f of x equals sine of 2x, because your quiz question was a lot like that, and you had trouble solving that equation. So just scratch that out and do this instead. So first of all, just say f of x is continuous and differentiable. Check. Okay, you got that. It's a sine function. It's this oscillating, nice little wavy thing. You know it's continuous, you know it's differentiable. What's f of 0? It'll be sine of 0, which is 0. F of 2 pi is going to be sine of 4 pi, right? Which is also 0. So condition 3, check. Okay. Now look for where the derivative, which is equal to what? Look for where that equals 0, or where cosine of 2x equals 0. And that 2x inside the cosine made a lot of you lose your minds. Like, oh no, it's a 2x there. So there is a way to solve this algebraically, but I think that you're probably actually better at graphing sine and cosine functions. So how many cycles does cosine of 2x go through in 0 to 2 pi? Goes through twice the number. Yeah, so usually it would go through 1 cycle in 2 pi, but since it's cosine of 2x, it goes through 2 cycles, right? Okay, so by pi, it's done with 1. And cosine will begin at, no, cosine begins at 1. Sine begins at 0. It's then across at pi quarters, it seems, right? By pi halves, it's down at -1. back up to 0, back up to pi. Same thing here, that'd be 3 pi quarters it crosses, down to -1, up to 0, back up. So you're trying to figure out where is cosine of 2x 0? How does that relate to the picture? Wherever the graph crosses the x-axis, that's where it's 0. There, 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 and there. So what are those numbers? Mm-hmm.
Plus pi n?
3 pi over 4. Be careful with 5 pi over 4 and 7 pi over 4. There's no pi n because you are within a specific interval. Does that make sense? As opposed to like saying all possible numbers. And I think it's plus pi over 2n. Do you also agree with that?
Yeah.
To get from pi quarters to 3 pi quarters, you add half a pi.
Yeah, I can see that.
You can see that? Now, another way to solve that, not the graph way, is to figure out that take the 2x in cosine. You know that regular cosine is 0 up there at pi halves, right? Down there at 3 pi halves, and then you account for the unit circle twice by going around this unit. You account for the whole 2x thing by going around the unit circle twice. And that would give you 5 pi halves and 7 pi halves. And then how do you get the x from that list? Divide by 2, and you're going to get x equals the same numbers we had up there. That's the way to do it if you want to not have to draw the picture. And that argument generalizes for like all sorts of stuff. I mean, if your argument inside had been 3x and had been difficult to graph. So, but the one that you'll see on your test will be similar to your quiz question, so you should be able to solve it by graphing if you like that way best.
Sorry, where did you get the pi over 2?
So I got the pi over 2 and the 3 pi over 2 by asking myself cosine of what gives me 0. And so I left the 2x as the what, and I said I know cosine is 0 at pi halves. Does that make sense? And then also 3 pi halves. And then because you have this 2x, you just go around the unit circle one more time. And so 3 pi halves plus another pi is 5 pi halves, and then 7 pi halves. And it'll give you the same answer. But personally, I didn't even think about it until recently that the graphing one really is the way to go with this. Okay. Is the next one the mean value theorem?
Yes.
Yeah. Woo. Okay, determine whether the mean value theorem applies to this function. So f is continuous and differentiable because polynomial. Check, check.
We need to state why.
No, just say you're checking those things, we're fine. Okay, also notice that f of x, probably easier to say it's equal to x cubed minus 2x squared minus 2x, right? Just by oh, it's just x squared, sorry. Yeah, I don't know why I got that 2 there. I like both added and multiplied at the same time. Oopsies. Okay. So we're going to find where f prime of x equals f of b minus f of a over b minus a. So first, what's f prime of x?
X squared
3x squared minus 2x minus 2.
Okay. Second, what's f of b minus f of a over b minus a? What number goes in for b? B, 1 goes in for b. What goes in for a? Over 1 minus -1. Okay. Say that again. Because of the interval, yeah, the a and b are the endpoints of the interval. All right, when we input 1, I think we get -2. Do you guys agree? Okay. When you input -1,
Hit 0.
you do, yes. Do you guys agree with that? Okay. All over 2. So f of b minus f of a all over b minus a is going to equal -1. Now you take the derivative and set it equal to -1. And that's what you're solving. Instead of solving derivative equal to 0, solving derivative equals whatever that average rate of change is. So we're going to solve 3x squared minus 2x minus 2 equal to -1. Or that's 3x squared minus 2x minus 1 equals 0, I believe. Is that right? Okay, I think that factors. And I hope it factors. I don't want to do the quadratic formula. I'm just too lazy this morning. I think +1 minus 1. Does that check out and multiply back to 3x squared minus 2x minus 1? Don't trust me because I'm not always right. You agree? Okay. So what numbers make that 0? Now technically the one thing, these must be in the interval a, b, like open interval with the same left and right endpoints. So in our case, that's the interval, I think, from -1 to 1.
So that's not included.
So one of them is not included. Which one is not included? 1. So only x equals -1/3. In the other questions that you had, the numbers were more obviously outside the interval, right? They cannot be the endpoints of the interval. It has to be within the middle. Because the derivative has to exist there, and the derivative doesn't exist at the endpoint, at least not for this class. So you can make derivatives at endpoints for different stuff, but we don't do it in here.
But doesn't the brackets used up top indicate that it is?
The brackets used up top indicate that you have a closed interval and the only requirement is continuous on the closed interval. The conclusion of that theorem definitely says in a b with open parentheses. So yeah, it is confusing, but the closedness is needed for the continuity part. And then it's not used in the conclusion. And because you're talking about the derivative, that's the reason. Okay. So section 4.3 wasn't ridiculously hard, I think, other than once we got past like all the technical reasons why stuff was true. How do you figure out where a function is increasing and where a function is decreasing? What do you use? You use the derivative, right? And where f prime is positive, then you're increasing, right? You're decreasing when f prime is negative. Okay, how about when is your function concave up? Second derivative is positive. Concave down, second derivative is negative. Inflection points, f prime prime has a sign change at a place where it is defined in the first place. Like asymptotes don't count as inflection points. And then determine whether a critical number is a local max or local min using either the first and second derivative tests. So the first derivative test, we had a number line and we plotted the sign of f prime. And if your f prime decreases, then increases, you've got a min. F prime increases, decreases, you've got a max. Now the second derivative test, I was just regrading some quiz corrections, so it's good to talk about. So for that second derivative test, you assume f prime of c is equal to 0, i.e. you have a critical number. And then if second derivative is positive, then f is, tell me, concave up or concave down? Concave up. So at x equals c is a min. The fact that the second derivative is positive doesn't mean max. The fact that the second derivative is positive means concave up. Think about what concave up looks like. That means it's a min, right? Does that? If the second derivative is less than 0, f is concave down. So at x equals c is a max. And just think about what, second derivative, negative, concave down means max, right? And then the c part, when the second derivative is equal to 0, the test fails. And that doesn't mean the point is a neither or it's a max or a min. In this case, it could go either way. So you just don't know what's occurring at that point then. You can't make any conclusions. You say inconclusive is better because undefined means doesn't exist somehow, but inconclusive just means you just don't know. So saying, cannot be determined is sort of better in some sense.
So would you say that then after you use the first and second derivative test to try to find it?
If the second derivative test fails, you would have to use the first derivative test to figure out if it was a max or min or neither. And the first derivative test, for the first derivative test actually always works. There's no special case that says that it doesn't.
So why would you take a second?
Well, the second derivative was easier for stuff like those applications that we had, where we were trying to show it was a max or a min, and you could just say, oh, the second derivative is a constant, and therefore we know we have the right thing. So it's useful for stuff like that, but you're right that if you're making a number line to check and see where a function's increasing or decreasing, you've done the work for the first derivative test. There's no need to use the second. So, but it's mostly for other applications and the way of looking at it. Okay. Now, this is a graph of a derivative. So on what intervals is the original function increasing? And on what intervals is the original function decreasing?
So it's increasing on -2 to 0 and 4 to infinity?
Yes. So remember that for increasing, you look for where is f prime bigger than 0, which in the context of the graph of f prime means where is that graph above the x-axis, right? So that's from where to where? -2 to 0, and where else? Yep. And then how about decreasing?
Is it decreasing on x equals 2 or?
No, it's a neither there, so you just leave that number out.
All right.
So negative infinity to -2, union 0 to 2, and 2 to 4. You have to leave out 2 because at 2 the derivative appears to be 0. You could also have sort of like translated this thing into a number line somehow by doing -2, 0, 2, 4, and then say sine f prime, and it'd be minus, plus, minus, minus, plus. Like that's what you would have looked at if you would have had an equation for f prime. I think you test numbers, okay, I test number here, the answer's negative. Test the number here, the answer's positive. Test the number here, negative, negative, positive. Just don't be confused and say that it's f, because it's not the graph of f. Okay, looking at that little number line that I made, what happens at -2? Does f have a max or does f have a min? Min. Min at x equals -2. How about 0? At 0, your f is going to increase and then decrease. So, bloop, bloop, makes a max. How about at 2? Your function is decreasing, levels off, decreases again. That's a neither point. How about 4? Min. At x equals 2. Neither. It's going to be a that kind of thing. I mean, ish, like a negative cubic. Okay. All right, when is f concave up? From 0 to 2. I'd have to think about it more. Okay, let me finish my explanation before I commit. So f is concave up if the second derivative is positive. F is concave down if the second derivative is what? Negative. Okay. So how about first here we figure out where the second derivative is 0. So when is f prime prime gonna equal 0? Look at that picture. At -1. And 3 and crap around a space. 5. You guys agree? Because the second derivative is the derivative of this thing, and the derivative of this thing is 0, there, 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 and there, right? Okay, so it says f prime prime's sign. So from here to here, f prime of x is increasing. So what's the sign of f prime prime going to be? Positive. How about the next interval?
1 to 2.
-1 to 1. Negative. And then 1 to 2 is the next place where it's positive. That's what you were saying. I get it. 2 to 3 will be negative, and 3 to 5, and then 5 forever, negative.
You're just looking at the slopes.
Yep, because it's the derivative of the derivative, right? And the derivative is the slope. Yep. Good thing to point out. Look at the slopes. So we're concave up, negative infinity, -1, 1 to 2, and 3 to 5. And we're concave down, -1 to 1, 2 to 3, and 5 to infinity. To infinity and beyond.
I think they're making another sequel to that movie.
How many are there by now?
Well, they're on 3 now.
Oh
so
my
it's gonna be
gosh.
4.
So inflection points at what x values? Uh-huh.
1.
1?
So 1, 2, 3, and 5.
Yep. You would only not have an inflection point if in that sign chart on f prime, there wasn't a sign change, but there's always flip-flopping, so it's at every point.
Why is it only just now asking us the inflection points? We couldn't have found the answer to the last question if we didn't know the inflection points.
Well, technically, until you make the number line, you don't know that they're all inflection points, they're just critical numbers. And they just happen to all be critical numbers in this case. Critical numbers that are also inflection points.
You're saying because it could have went positive.
Because they could have went positive, positive, or negative, negative. They don't in this case, but you are right that they're definitely very related. The list, the second one is a subset of the first list in some sense. Okay. All righty. Trig function. So find the open intervals on which this function is increasing or decreasing. Okay, x plus 2 cosine x on the interval from -pi to pi. So if you're going to talk about increasing or decreasing, you need to look at the what? Derivative. And the derivative is
1 plus 2 sine.
almost 1 minus 2 sine x, or 1 plus 2 times negative sine x, right? So set that thing equal to 0, which means we're solving sine x equals a half again, which I think we did earlier today, didn't we? Yeah. So if we're on negative pi to pi, okay, negative pi. So I think if you put 0 in the middle, the first place sign is 1/2 relative to 0 going counterclockwise is pi 6, right? We discussed that it was this angle and this angle, right? So pi 6 Gesundheit and 5 pi 6. So these are actually critical numbers. Are there any numbers on this part of the unit circle where sign is positive 1/2? No. Okay, so don't have any there. With trig functions, the easiest test numbers are going to be things like whole pies and half pies and 0, right? So what's the number you can test between negative pi and pi 6? Even easier, you could test 0. And I think 3 pi halves isn't actually in your interval at all. You could test negative pi halves. Does that make sense? Okay. But it would yield the same answer. If you plug 0 into this guy, I believe you just get 1. So the kicker, though, is that your f prime is positive. Okay, what's a good test point between pi 6 and 5 pi 6? Pi over 2. And at pi over 2, the sign is 1. So you'll have 1 minus 2 will make negative there, right? And then I think you can actually test pi, even though it's an endpoint, and you're going to get that this is, f prime is positive there.
That's kind of cheating though, isn't it?
It always works. You can test the endpoints as long as the derivative isn't 0 at them. It will work. So technically it would actually work if you tested any number up until the derivative is 0 again. It'll give you the right conclusion. But the endpoints are definitely
It seems like
safe.
those specific spots is where the signs flip.
Yeah, but the sign doesn't flip at the pi and negative pi because the derivative isn't 0 there. So where is this function increasing? Mm-hmm. Negative pi to pi 6 is correct, yep. And 5 pi 6 to pi. And it's decreasing from pi 6 to 5 pi 6. Now, I'm not going to be picky about the endpoints of the interval, because it isn't even clear to me exactly if it was to include negative pi or not, if it technically counts. I don't really care, but the middle points, definitely the derivative is 0 there. Those are definitely not included. Okay, so that's the only thing. Okay, I think part B relies heavily on part A. It says find the local maxes and local mins, right? Okay, so what happens at pi 6? Is it a local max or a local min?
It's a max.
It's a max because your derivative is in positive, negative, so f increases and decreases. And at 5 pi 6, you're going to have a min. Yep. Okay, so f of pi 6, which is equal to, we'll figure it out, that's going to be a max. F of 5 pi 6, what it's equal to is going to be a min. So that's going to be pi 6 plus 2 cosine pi 6. So pi 6 plus 2 times, what's cosine of pi 6? Square root 3 over 2. So that's going to be pi 6 plus root 3. Okay, good enough. And this will be 5 pi 6 plus 2 cosine of 5 pi 6. And what is cosine of 5 pi 6? Good, so that's 5 pi 6 minus root 3. all right? Okay. Yay. Not that bad, right? Because you can now unit circle. Better than I could when I was in Calculus 1. Okay. Find the open intervals on which the function is concave up and concave down. So for this, we need the second derivative. The first derivative was 1 minus 2 sine of x, right? So what is the second derivative? And that negative in the front definitely matters, so be very careful that you don't like disregard it. Okay. So in the interval from negative pi to pi, where is the cosine 0? In this positive direction, it's 0 at that point right there, isn't it? So what point is that? Pi halves. And in the negative pi direction, when is the cosine 0? Negative pi halves, exactly. Yay.
Is that, I just divided the -2?
You can divide the -2 away and say you're just looking for where does cosine equal 0, right? But the reason I'm being a bit careful is that when I plug my test numbers into the second derivative, that -2 is going to affect the sign of what's happening at those points. So you can test negative pi. It's totally okay. What is cosine of negative pi?
Well, negative.
-1, which times that -2 makes +2, so you're concave up there. Yeah,
Why could you test the endpoints in this one again?
because the derivative isn't 0 at them. How about in between negative pi halves and pi? What's a good test point? 0, yep. So when you plug in 0 into cosine, you get 1, so the second derivative is negative there. And plugging pi in is the same as plugging in negative pi. You get that the second derivative is positive there. So f is concave up, negative pi to negative pi halves, and pi halves to pi. And f is concave down from negative pi over 2 to pi over 2. The only time you couldn't test those endpoints in something like this is if the derivative was 0 there. And if you're uncomfortable, you could test something in the middle, like testing -3 pi quarters isn't going to be super terrible either, is it? Because you can do the quarters really easily. So I would suggest first trying to do halves and wholes, and if you can't do halves and wholes, do quarters. Okay, so how many inflection points are there? 2? They're at negative pi halves and pi halves. So the inflection points, so f of negative pi halves and f of pi halves. And unlike maxes and mins, these aren't classified. Going concave up to concave down doesn't have a different name than concave down to concave up. Just tell me what their y coordinates are. So that's negative pi halves plus 2 cosine negative pi halves. And this one's going to be positive pi halves plus 2 cosine pi halves.
Isn't it just pi over 2?
I think this one's just negative pi over 2, and that one's just pi over 2. Because cosine of both those half pies is 0, isn't it? Okay, so those are your inflection points. There's that one, and there's that one, or the y coordinates. Yay, trig. All right, section 4.4 was this L'Hopital's rule thing. So what did L'Hopital's rule say? The limit as x goes to some number a, f of x over g of x is equal to the limit as x goes to a of what over what? F prime over g prime. You don't need to account for the fact that g is in the denominator, Okay, you just differentiate the top over differentiate the bottom. You don't use the quotient rule, you just do top derivative over bottom. You do what you wish the quotient rule was. And this only applies if it's a 0 over 0 or infinity over infinity limit. And if that condition is not met, then the rule breaks down and falls out the window, and you can't use it. Okay. It's a great rule. I love it. So with this first one, is the limit a 0 over 0 limit, so can we use this rule? When x goes to 0, what's 3 to the 0? 1. What's cosine of 0? So we've got 1 minus 1 over 0. Is it 0 over 0? Yes. Okay. Limit x goes to 0. What's the derivative of the numerator? Mm-hmm. Mm-hmm. Plus sine x over. And you should check. Now when I'm at this stage, can I plug in 0? And technically, you do have to use, like you cannot drop that limit sign. And it's a bit of a technicality, but this function doesn't equal that function. Their limits are equal. They're not the same thing. Their limits are. So it's a little like using the right mathematical language. Can you input 0 now? You can. This becomes ln of 3 times 1, right? Plus 0, and I believe secant of 0 is 1. Because secant of 0 is 1 over cosine 0, and cosine 0 is 1, right? So this is just equal to natural log 3. That's what that limit is. And there's no other way that you guys would know how to find that limit. I mean, there's no like factoring or algebra that can make that baby happen. Okay, part B. Is this a 0 over 0 limit? Hmm?
There's an
We have
I
an
on
eye on
ours.
ours.
You have an I on yours. Is it an accidental I?
Well, it's still 0 times root of negative.
Oh, there's not supposed to be an I there. Ignore that I. The I, yeah, no. No, it's just supposed to say what this says. If I had an I there, it was totally a mistake.
I thought calculus didn't deal with.
No, we don't usually deal with imaginary numbers. So when you plug in 0 in the numerator, what do you get? 0. What about the denominator? You get 0 over 1. You can do that without any calculus needed. Well, it's 0 divided by 1. That's one of those ones that's okay, as opposed to being a no. And even if it was 1 over 0, you couldn't use L'Hopital's rule to deal with it because it wasn't a 0 over 0 limit. So you're just SOL. Shoot, out of luck. Darn it. That's it. That's it. You're just darn it out of luck. So watch out for stuff like that. Don't apply the rule blindly. Ask yourself, is it 0 over 0 before you begin?
You know, I like George Carlin's mnemonic better. SOL and JWF. S out of luck and jolly well F.
Oh, geez. Okay, moving on. So this one is not 0 over 0 to start, is it? What do you think you have to do? Find a common denominator, because what else are you going to do, right? I've got no other ideas. So that's going to be x ln x minus parenthesis x minus 1 over x minus 1 times natural log of x. It's because some evil, mean person wanted to make you use the product rule that this happened to you. I don't know who that person would be. Does everybody agree with my common denominator step? God, I hope it's 0 over 0 now. I think it is, though.
I hope it's 0 over 1.
The natural log of 1 is 0.
Natural log of 1 is 0. So we have 0 minus 1 plus 1 in the numerator. So 0 minus 1 plus 1. So that's 0 over 1 minus 1 times 0. So it is a 0 over 0 limit. Okay, so you use the L'Hopital's rule. So what's the derivative of x natural log, I'll do that one in blue, x natural log of x? So it'd be 1 ln x, right?
1.
Plus x times 1 over x, which is 1. Don't forget, that's x over x, which is 1. Minus 1 plus 0. What rule do we have to use to take the derivative of the denominator? Product again. So 1 ln x plus x minus 1 times 1 over x. So I'll simplify a little bit. I think the numerator is just ln of x. Do you guys agree? And the denominator is ln of x plus x minus 1 over x. Actually, let me change that denominator ever so slightly. Let's make that denominator into, 1 minus 1 over x. Is that okay? Because I just took this 1 over x and just distributed it, right? 1 over x times x is 1. Okay. Because I think it's still 0 over 0. So do you agree with the algebra?
Yeah,
Okay, and do you agree that it is still 0 over 0?
yeah.
Okay, yes, Rachel?
Where did the negative minus 1 go and then your negative?
This x times 1 over x is 1, and then it takes away that takes out the other negative 1. But I think one more time will be enough. I just hope so. Okay, so what's the derivative of natural log of x?
Over x.
And then 1 over x plus 0. What's the derivative of that 1 over x there? It'll be positive 1 over x squared. Do you agree with that? And now you can input 1 and you get 1/2. You buy that? Is that okay? All right. I think there was a question like that on maybe it was on the test or a quiz, and the number of people who couldn't say that x times 1 over x was 1 was staggeringly high. Don't forget. Pressure. Okay, let's do this one, then we'll take a quick break. So a particle moves up and down the y-axis with this position function. Find the velocity and acceleration functions. So what's the velocity? First derivative, which is great. And the acceleration function is the second derivative, which is, yep.
Would it be correct to simplify those?
Like to factor out the greatest common factors. If you want to, you can, but you don't have to yet. You might have to eventually. I think we will have to eventually. Okay. Has everybody got that? So when is the particle moving up and when is the particle moving down? So the particle is going to be moving up when the velocity is positive, moving down to the down, oh my gosh, when the velocity is negative. Oh, there's another one. Oh, man. When is the particle moving up and when is the particle moving down? It probably was a modified left and right thing, to the right and to the left. That's where this came from. I copy-pasted and didn't read. Okay, so your velocity equation was 3t squared minus 6t plus 9. If you want to figure out where the velocity is positive and negative, set it equal to 0, and we're going to make a sign chart for it. So take out a 3.
Minus 12.
Oh, thanks. That's going to affect everything. So t squared minus 4t plus 3. Is that the correct greatest common factor? Yeah? Okay, how does that factor now? T Mm-hmm. Okay, so v of t's sine 1, 3. Technically, we go from 0 on up. So initially, is the velocity positive or negative? You could test 0, right? Positive. How about between 1 and 3? And then how about positive? Okay. So to the up, that's just me being silly, on the interval from 0 to 1 and 3 to infinity. How about going down? So up, down. So the particle, actually, how could you tell me where it would start? Yeah, plug in t equals 0 and your particle actually begins at 0. Does that make sense? Initially, it goes up some amount to find that I've got to plug in 1 for t. What happens after it goes up? And it goes, after that it goes down. You have to plug in t equals 1 to figure out how far. What would you plug in to figure out how far down it goes? You plug in t equals 3, and after that point, what happens to your particle forever and ever and ever? Nope, it goes up because the velocity is positive. Velocity is speed plus direction, right? And to figure out specifically how far up and specifically how far down, you've got to plug those numbers into your position function. But that's the same kind of diagram we drew earlier, isn't it? This part right there where we began was when t equals 0. It just happened to also be at y equals 0 at that point. But it goes up, down, back up forever. And really it does this in like a bounce up, bounce down, bounce back up. It doesn't actually go out at all, but you just can't see that if I draw the lines on top of themselves. Okay. When is the particle at its maximum or minimum height? So because of this diagram, you can think about this picture in your head, does this particle have a maximum height? Globally. That's a local max. Does that make sense? But because this particle goes up forever and ever and ever, it's not like a global max. Okay, so technically speaking, there is no maximum. Like there's no max height because like it doesn't say find its local maximum height, it says find its maximum height. There is no maximum height. How about,
Would you want us to put the local max?
Just the question asks for just the act when it says like, what is its maximum height, then there just isn't one. If you put the local, I don't think I'll dock you. And then the minimum height, when does this occur? At t equals 3, and the height is y of 3, like what you get. And I guess I did just say when, but let's just for kicks figure out what that height was. So that will be 27 minus 6 times 9, yep, plus 27, is that right? Because it'd be 9 times 3. So that's 54 minus, okay, so that is 0. So what we know then is that this particle starts at 0, goes up to something, goes back down to 0, and then at that point in time goes up forever. Okay. Well, the minimum just occurs twice, right? It still is the same, like the lowest this point gets is 0, it just happens to happen twice. I guess it also, you have to be a teensy bit careful that this number that you got when you plugged in 0 wasn't below the next number. Does that make sense? Because you could have had a picture that looked like this, theoretically. Up to a point, goes down to a point, and then goes up forever. That's possible, and that lowest point could have actually been your starting point. So really, I mean, I need to be careful that I don't do that to you, but asking you for a diagram would be a way around that as well, right? It's almost never very hard to plug in 0, is it? No, there would be a min, it just would be this first number. It'd be the starting position is the min. Like, think this particle bops around, it goes up and down. When is it lowest? It's lowest in the beginning. It just doesn't, it's just kind of like when maxes and mins on closed intervals aren't at middle points. Sometimes they're at endpoints. Okay, let's pause for a second, take like 5 minutes. It's a sphere and a cuboid.
The one thing that got me on that question, because it was a box, I didn't think of it as like a rectangle.
I guess I figured like cardboard box.
Yeah.
We can do a few of those if we have time, like I don't mind, okay? So sketch curves, this really is just kind of a summary of all sorts of stuff. Oh shoot, I need to write down my derivatives. Okay, find the domain. So what are the two things x cannot be in this case? 3 and -3. And if I don't say interval notation, whatever, no interval notation. Okay, find the x and y intercepts. So x-int set y equal to 0, y-intercept set x equal to 0. So if you do the first part, 0 equals 1 over x squared minus 9. That'll give you 0 equals 1, which is crazy talk, right? So there are no x-intercepts. Like, zilch. None. Is that because you try to find the x-intercepts by setting the y to 0 and you get a no solution equation, which means there just aren't any to begin with? That kind of is a contradiction thing. You say, okay, well, if there are x-intercepts, the y must be 0. But when I do y equals 0, I get craziness. 0 is not equal to -1, right? That's not true. Or 1. What is the y-intercept? X is 0. The y is, what'd you say? -1/9. Okay. Symmetries, periodicity. Plug in -x, you get 1 over -x squared minus 9, which is the original function. Nope, you can just say even. If I don't say write your work, you can just tell me you can see it right away. Okay, determine the asymptotes. So where are the vertical asymptotes? And you have to specify x equals. I will be picky about that because I care that you know vertical lines are x equals things. HA is y equals 0. Technically, that's found by doing the limit as x goes to positive and negative infinity of this function. But because you have 1 divided by a big number, that's making 0. Okay. You can use that too, definitely. Increasing, decreasing, and find the local max and min. So I didn't give the derivatives, but I really should have. This is the same thing as x squared minus 9 to the -1st, right? So the derivative using the chain rule is -1 x squared minus 9 to the -2 times 2x. Or -2x over x squared minus 9 squared. If I was high school, I would have taken that phone and answered it.
This phone's still on his desk though.
It's got 2 of them,
Oh gosh.
just like a high school student.
Just a work phone.
Yeah, one could be a work phone. Okay. Or you could just have no phone and live without. Life is so great. Okay, then find the sign of the first derivative, and when you plot numbers on the number line, you must also include your asymptotes because things could have changed there. Okay, so you plug in a number to the left of -3, will f prime be positive or negative? Positive. And then times another negative number makes a positive, right? The denominator won't ever matter because the denominator will always be positive because of the squared, right? How about plugging in something like -1 to test? Also positive. And then I think we're going to get negative after that, right? Okay. And the number line is not enough. You have to tell me you can make the number line into intervals. So f is increasing -infinity, -3, union -3, 0. F is decreasing 0 to 3, union 3 to infinity. You do have to write them as intervals.
We took out the threes because they don't.
The 3's are asymptotes. And even if the derivative had been 0 there, you still wouldn't include them. So they don't ever get included here. Because they're either derivative being 0 or asymptotes. That's the only way they'd ever get listed anyway. Yep. Okay. Intervals of concavity and inflection points.
Local max.
Oh, local max min. Okay, thanks. So are -3 and +3 candidates for local max and min? No, because they're asymptotes. So who is the only candidate for a local max or min? 0. And is that a max or a min? It's a max. F of 0 equals -1/9 is a local maximum. I didn't mean to make you guys do the quotient rule for this, so I'm going to use my calculator and get the second derivative. On the test that I wrote, I already did this, so x squared minus 9. Okay. For g, the second derivative is 6 times x squared plus 3 over x squared minus 9 cubed. And this is why you don't get to use TI-89s, because it did this in 5 seconds. Okay, so what numbers go on your number line for f prime prime's sign? Plus and minus 3. Does the numerator ever equal 0? For real numbers? No. And so imaginary numbers, they don't happen in this class. Okay. So test some things. Like say we tested -4. Would the numerator is positive. The denominator is also positive. So we're concave up. What if you test 0?
It's negative, yeah.
Because of the denominator, right? And then testing something past 3, like 4, you're going to get that f prime prime is positive again, right? So f is concave up on -infinity to -3 and 3 to infinity. F is concave down on -3 to 3. Inflection points, are there any?
3, -3. Oh,
They don't count, so technically there are none. There is a change of concavity that happens at the asymptotes, but they're not points on the graph. Okay, sketch the curve. Attempt to draw straight lines. Ooh. Okay, so you have vertical asymptotes at positive -3, so let's just sketch those in. When you plug in 0, you got -1/9, right? Okay, so we'll just say that that's -1/9. I deem it so.
Concaved up, right?
Hmm?
Concaved
we were concave, I didn't write down the rest of my work somehow. So were we concave up or concave, and what were we doing? When were we increasing? We were concave down in the middle? And we were increasing from negative infinity to negative 3. Okay. And we were decreasing from 0 to 3 and 3 to infinity, right? Okay. So I believe that means that your picture in between negative 3 and 3 looks like this.
Shouldn't you put the y equals 1 asymptote in there?
There's a y equals 0 asymptote, actually.
Yeah.
Okay. And you can think about that when you plug in numbers like 1, you're going to get 1 over negative 8. So negative 1/8 is down there. 1 over 2. So it's going to end up being that kind of shape. And what if you plug in like things like 4 and negative 4? You get 1 over 5, so positive something. So it'll look about like this. And has that even symmetry, about like that. Ugh, I hate curve sketching. I think optimization problems are so much more fun. Okay. So find the rectangle of maximum area that can be inscribed inside of this parabola with its base along the x-axis. You had almost the exact same question on your quiz, except for your equation was like 3 minus x squared. So what does 20 minus x squared look like roughly? It's an upside down parabola shifted up 20. So 20, and it's something like this shape. Okay. So pretend that this is like, I don't know, a lot or something like that. You've got this weird shaped lot and you want to build the biggest house possible on your lot out to your boundaries. And your house is going to be rectangular, not funny shape. It's a boring house. So there's your biggest rectangular shape. Because you could draw a rectangle like that. Your rectangle could also have been sort of squat and wide, right? So the question is, which one is the best? How do you enclose the most area? So the area of that rectangle, this distance is x, this distance is y. So if you do x times y, it finds that half of it. So what's the total area then? 2xy. And your y has a specific relationship. That's a y on this curve, right? Which means that the y is equal to 20 minus x squared. And you want to find the max. And you know calculus now, so you're like, oh wow, maxes happen where the derivative is 0, right? Or mins as well, but you know, you're just a place to start. But since you know calculus really well, you're like, I don't want to use the product rule, right? 40x minus 2x cubed, right? Woohoo! So the derivative is equal to what? Set it equal to 0. So 6x squared equals 40. X squared is 20/3. So it looks like x equals root 20/3. Okay. So the base is x equals root 20/3, technically times 2, right? How would you find the height?
Put it into y.
So y would equal 20 minus root 20/3 squared. So 20 minus 20/3, I think is 40/3. Do you guys agree with that?
Oh, yeah,
Okay, good.
But why did you decide to make the base 2x and not just assign x to the whole thing?
Because x in this context, like, has meaning since you're on an x and y axis. So you can't, because it already has meaning in this equation.
Okay.
So because of that, like, implied definition of what x means, you can't let the base just be x. But that's a good question, because you're right, you could just define a new variable. That's the other phone, or is that somebody else's phone?
That was, yeah.
Okay.
Why did you square the root 20 over 3?
Oh, because I was finding the y coordinate, and the y coordinate is given by 20 minus x squared.
Thank you.
Okay. Find the rectangle of maximum area. So I guess that means give me the dimensions. So this rectangle is base 2 root 20 over 3, height 40/3. One more thing. On your test, I will ask you to justify. So how do you justify and tell me that you know it's actually a maximum? What's the easiest thing to use? So the second derivative is negative 12x. And the second derivative with root 20 over 3 plugged in is negative. So A is concave down, and this is a max.
See someone take those dimensions to any carpenter in the world.
Well, you give it an estimate. You wouldn't actually give those dimensions to the carpenter, but I mean, you find the best one and then you approximate it. And tons of real world problems don't have nice solutions. So,
What is CV?
concave down. It's a record sort of like thing. I'm just kidding. I'm just being sarcastic. Sorry, can't help. Yes, exactly. Okay, find the point on the graph, f of x equals x squared plus 1 squared, that's closest to the point 5, 3. So for this, you have to know the distance formula. What is the distance formula? Okay, if you made a mistake on your quiz, it was you made that plus sign in the radical a minus. Okay.
So you can just disregard the square roots?
You can, yep. So our distance will equal the square root of, we'll say, x minus 5 squared plus y minus 3 squared. And I'm going to take that f of x and write it as x squared plus 2x plus 1. Or the distance is the root of x minus 5 squared plus x squared plus 2x plus 1 minus 3 squared. And with these distance questions, you can define your function f of x as the distance squared. And you can minimize that instead. And that's going to be easier. Only the inside matters. It's just going to be easier to take the first derivative of, and then it's also going to be easier to use the second derivative test to verify that you have the right conclusion. So the reason is the inside's the only stuff that actually matters.
And you did d squared because you squared both sides to get rid of the root?
Yes, exactly. Yep. Okay, on your quiz, the question was significantly simpler because you didn't have this like awful squaredness. So to take the derivative with this guy, let's use the chain rule. Does that make sense? So f prime of x, what's the derivative of this first component?
2x minus 5.
times 1, right?
Yeah.
And then plus 2x squared plus 2x minus 2 times 2x plus 2. Okay, now assuming that we can all multiply that, I just don't have the patience. 2x minus 5 plus 2 times x squared plus 2x minus 2. There's so many 2's, I'm going to lose track of them all. 2x plus 2. That gives you 4x cubed plus 12x squared plus 2x minus 18. And you guys don't know any great methods for solving cubics, do you? This is a question that I wouldn't put on your test, FYI, okay? If you set that equal to 0 and solve, believe it or not, x equals 1. That was obviously a problem doctored to work, right? So if you were at home and you had calculators and things to solve this, I mean, there is a technical way that you maybe learned in Algebra 2 class. It's called the rational roots theorem, but it's tedious and it sucks. It's awful. So given that we actually have technology, a way to look for where that 0 is to graph it and look and see where it crosses the x-axis. I won't give you one that requires that on the test, okay?
Okay, so
But my main-
It's gonna have one that's about like.
Yeah, like the quiz question, yeah. But it won't be as, the details won't be as tedious. Does that make sense?
Could be something that's like a second degree.
Yeah, second degree, a linear thing, like there was in your quiz, right? Something you can actually do quickly. So, but my main point was that what function do you use to set this up? Because that relationship is pretty much, is always the same, right? Use the distance squared. So the x-coordinate is 1. The y-coordinate, f of 1, is going to be 4. And then to verify that it's closest, you'd look at the second derivative, which is 12x squared plus 24x plus 2. And when you plug in 1, you get some positive number. So f is concave up, and thus f has a min at x equals 1. And is a minimum what you wanted? Closest means smallest distance, right? So the details of this to this and then this to solving definitely won't be on the test with a question that's that difficult, more like the quiz one that you had. That damn farmer again, I know. And this one has a little bit of trickery because you can't actually use 1.5. You have to convert that. You have to make that into 1.5 million with zeros or it won't work out well. Like, I couldn't make it work without that. So he wants to make a rectangular field and then divide it in half.
When you do problems like this, does it really matter which way you run the fence? Down the
Mm.
middle?
No. Oh, well, you can't run it at a diagonal.
Well, I meant like either.
No, that's the same thing, or this is the same thing. But when it says all pens are parallel and it says to make 4, this isn't the right thing. Does that make sense? That's
Yeah.
not all pens being parallel to each other or side by side. Okay, so I'm going to call this whole side x and this whole side y. So I just use P for perimeter, even though it really isn't perimeter because it's around all of the sides. How many x's are there? 2. How many y's are there? 3. If anybody made a mistake on their quiz, it was that they missed one of those. Like they just didn't count. I don't know how that happened, but it does. Do we know how much fencing we have? No. No. What's the 1.5 million?
It's the area.
That's the area. So the area is equal to xy. How many zeros is 1.5 million going to have?
5.
Mm-hmm. Okay.
You should go 32M.
Okay, so let's just solve for y there. Y will equal 1.5 million over x. And my p is 2x plus 4.5 million over x.
Could you keep it as a decimal? And then add-
No, it doesn't work. I tried. It's because of the square units, because of the complication with the square units, so definitely not. Okay, so can you take the derivative of this thing now to maximize or minimize it? What's the derivative of the 2x going to be? 2. How about the 4,500,000 over x?
Negative 4.5 million over x squared.
Mm-hmm. So p prime will be 2 minus 4.5 million over x squared. Set that equal to 0. So 4.5 million over x squared equals 2. 4.5 million equals 2x squared. X squared is, what's half of 4.5 million? I think it's 2 1/4, isn't it? 2,250. I think that must work out nicely. Do you guys know what the root of 225 is? I think it's 15. Is I think, does 150 make sense, or is it? It's 1,500. Yep. Actually, then the y is going to be pretty easy, isn't it? Y is 1.5 million over 1,500. Cancel some zeros. I think that's going to be 1,000, isn't it? I said 1,000 and wrote 100.
And we're back in feet.
We're back in feet now. Yep, these are feet because they're dimensions of the pen. And then how could you check that it was a min? Second derivative, yep. The second derivative would equal, I think, 9 million over x cubed, wouldn't it? And so p prime prime of 1,500 is positive, so p is concave down, thus, no, concave up, sorry. Positive concave up. Therefore, you have a maximum at the x equals 1,500.
Concave up is.
Oh, it's a- Yes, it's a min, which a min is what we wanted anyway, wasn't it? Yeah.
Does that
Okay.
equal the minimum cost of the fence? If it's
Well, the minimum cost of fence was when you use the least amount of fence,
Yeah.
assuming that you can buy fence by the yard or by the foot, which is not always true. Right? Some places you have to buy a whole roll of fencing and you're stuck using a fixed amount. In which case you take your fixed amount and you want to maximize the area because you know how much fence you have. Does that make sense?
The rolls should be limited anyways.
Yeah, but this one is the kind of thing where you say you know how much area you have and you're assuming you can buy fencing in such a way that you could get exactly what you need. Which might be true if somebody can build you a chain link fence, actually. It wasn't true with my duns that they then broke, but that's a different story. Okay. So this is the economic stuff with, so you have a baseball team that plays in a stadium that holds 55,000 spectators. When ticket prices are $10, the average attendance is 27,000. When ticket prices drop to $8, the average attendance rose to 33,000. Find the demand function, assuming that it's linear. So the thing with cell phones and this demand function, it's okay. X is always equal to the number. Vibrate, guys. Phone's on vibrate.
Let's just check it out quick. picture.
Thank you. X is always the number of things you're selling in this context of these problems. In this case, X is the number of tickets. And the demand function, this is what they call the price function. It tells you the price given a number of things you're going to sell. So what price will it be if you want to sell this many? And we're assuming that it's linear, so which means we've been given two ordered pairs. So the first X is if I have how many tickets?
7,000.
And the cost of those tickets, or the price, was, and the other one is 33,000, and the cost of that was 8. 8 minus 10 over 33,000 minus 27,000, negative 2 over 6,000? Is that right? Sure.
Is there a reason to go if ticket price was your X?
You can do it that way, I just didn't, and the textbook doesn't, and so if it's asking for the demand function, like on a WebAssign question, it's gonna want you to do it this way. If you phrase it that way, you've gotta think about it a little bit differently, but it can work, it's possible. Okay, so then y minus 10 equals negative 1 over 3,000 x minus 27,000. Now, I think that's going to work out to be a nice number. Because all the zeros cancel, and you get 27 over 3, right? So plus 9, do you guys agree with that? So this is, the demand function is negative 1 over 3,000 x plus 19. But how they define that demand function is that it is y is the price. So that's just the book's definition and their way of doing it. Okay. We kind of did stuff like that in the first chapter, didn't we? Like a little bit. It was with like making chairs and stuff, right? All right. How would you set ticket prices to maximize revenue? So revenue is X, which is how many things you're selling, times P of X. So how many times price. So X times negative 1 over 3,000 X plus 19, or negative 1 over 3,000 X squared plus 19X. So that's going to be negative 1 over 1,500 x plus 19 is the derivative. Set it equal to 0. I got 28,500. That's not the price, obviously, right?
Okay.
What does X stands for? Number of tickets, yeah. So then how would you figure out the price? Plug it into the one from part A, the P. So P of 28,500. So that number times negative 1 over 3,000 plus 19. So I got 9.5. Does that sound like a more reasonable price? Yeah. Yeah, 950. Okay. That's it.